Alright, good morning. Here we are for yet another lovely day of CENG 3306 Mechanics of Materials. We are only going to have one lesson today, a rather long one, lesson 32 on prismatic beam design. So, let's get started. Got a lot of material to get through, and this is going to be quite involved, but that's okay. So, for our last day of the week, we will do a single lecture instead of two. That one lecture will be a bit long. So let us get started. Well, first let me make sure we're recording good. We are, and good. Okay, so we're working through sections 11.1 and 11.2 in the Hibbeler text, and we have a few learning objectives today. 1, design the most efficient beam for a given set of loading. Locate the maximum flexural and transverse shear stress in a beam. And 3, use Moore's circle to develop principal stresses at any point of a beam. Okay, so let us do a bit of review first. I want to gather up a few sort of tools in our toolkit that we will use through our work today. So let us review a few things here on both bending and shear stress. So consider a rectangular cross-section in a beam, or just any cross-section in a beam. Let's look at this. I want to draw a beam and look at the state of stress at different locations within it. So I'm going to draw the neutral axis here. No, I think I might actually draw this a little bit bigger. Because while paper is cheap, digital slides are free. We have infinite space, more than we could ever need, just by adding more slides, etc., etc. Okay, so we have our neutral axis here. In this rectangular beam, it would be at the center of the beam, but obviously for other beams, non-vertical or non-symmetric beams, it could be located at any height. And I'm going to draw sort of a pseudo 3D beam here. It's a 3D-ish beam. There we go, 3D-ish. Now, a few things. So let me show the neutral axis. Let me label that. I've drawn it. Let me label it. The neutral axis, again, is the location where bending is 0. There is no tension or compression from bending. It is simply 0. There will be no stress or strain from bending at the neutral axis. Then we have, and I'm going to look at a point C here. Point C. Then I'm going to have a location somewhere in the middle that I'm going to call point B. So this could be anywhere along the height. And then finally I'm going to have a location that I'm going to call point A, which would be located at the outermost fiber. Which would be located at the outermost fiber or at the top or the bottom of the beam. And we should keep in mind a few things. I'm going to have a few variables here. Well, one, I'm going to have YB, which will be the actual distance from the neutral axis of point B. And then I'm going to have C, which is the distance to which is the same C we always have as a variable anyway. This is the distance from the neutral axis to the outermost fiber in the beam. Okay, so let me draw this across. I'm going to draw a series of diagrams here, and I want to compare. So in this lesson, this is where we really sort of bring together all what we've learned in the past few days over shear and bending stresses in beams. We're gonna bring it all together. Bring it all together, apply it all at once, see how they see how they interreact, really? That's not a word. See how they interact and interrelate. That's the word I'm looking for. English be hard. Okay, so here we are. Let's say I have something like this. This would be the bending stress. This would be the bending stress in the beam. except it would be linear, not this, except it would actually be linear, not this, whatever it is that you're here.
Linear.
Yeah, squiggly linear is approximately linear. Etc. So we have this kind of linear-ish bending stress. And then we have a sigma in tension, our maximum sigma in tension, which will be positive. So I could actually say just sigma here is positive, and sigma here, the one associated with compression, will be negative. And all of this together, the vector sum of all and applied over dAs of all of this stress is going to be our moment here. Then, if I draw the shear stress distribution, I'll end up with a parabolic relationship, something like this that we saw yesterday. Hey, that's not so bad. With a shear stress tau here, and all of the shear stress will come together, the vector sum of all their stresses multiplied by dAs. If you did the integral of that, all of this would come together to form our shear vector V, the shear from our shear and bending moment diagram. Now, from this, we can actually see a few things about the state of stress. So, state of stress, basically the state of stress varies about the length of the beam. This is what we know from statics. Obviously, the shear and bending moment, they vary across the length of the beam. So if the shear and bending moment are changing, the state of stress are obviously going to be changing. So that's fairly obvious. But they also vary across the cross-section, vary about the cross-section. So different locations in the cross-section will have different states of stress. So really, let me erase some of these so I have a little more room. I can draw different stress blocks for these different locations A, B, and C. So let me do that. Let me draw one for A. I'm going to draw 3 stress blocks, one for A, one for B, and one for C. My perfectly square stress blocks. Squarish. A here. Oh, let's use all the pretty colors. B and C here. So let me show my stress elements, or sorry, my stresses here. So let's look at point A. At point A, the shear stress is actually 0. At the outer surface, the shear stress is going to be 0, but the bending stress is going to be at a maximum. So we only have stress in bending. This is just going to be sigma x equals mc over I. Then at B, we have a combination of shear and moment. So at any point between A and C, we're going to have a combination of shear and bending. So we have a more complicated state of stress. We have a more complicated state of stress. We have these combined together, like this here, like so. So tau xy equals V, the Q at B, over IT. And so we have the shear stress vectors like this, and our normal stress vectors like this, where sigma x is equal to m yb, m times yb over I, like so. And then finally at point C, at the very neutral axis, or in this case the very center of the beam, we have only shear stress. So we have an element that is only loaded with shear vectors, and this is simply going to be tau xy equals V QC over IT. Okay. And again, point of note, the sign convention for shear, for this case anyway, for our beams here. Sign convention for shear. Sign convention for shear here when we're working with beams, the sign convention for shear is going to be this. This is going to be positive and this is going to be negative, like so. That makes sense? Okay, so it's a bit different. It's flipped when we're dealing with beams, yes. Okay. Okay, so the question is then, how do we actually design beams? How do we actually design beams? In other words, where do we check for critical stresses? Where do we check for critical stresses? So there are an infinite number of possible points we can check. We need to find we need to find which points are critical when designing beams. Okay. So let's see. The question is, when we're doing, we need to look at where do we check for principal stresses. For principal stresses. Where do we check for principal stresses? And we check at the critical points. So the answer is we check at the critical points. At critical points. So what are the critical points? Well, so we just answered a question with a question, essentially. So the critical points, we have a few along beam locations. Beam location and cross-section location. So basically we can see the state of stress varies along the beam and the cross-section. So we're going to have locations where we need to check that are critical for each. And we'll basically need to check all the combinations therein. So let's say we have the point of 1, let me do this here, let me give you 3 for each, 2, 3, and 1, 2, 3. So this is where steel design really gets complicated. There are, along the cross sections, there are 3 locations to check. One is the point of max moment, Mmax. The next is the point of max shear, Vmax. And the third is the M and V max combo. So where they are largest together. And we'll see what that means. Hopefully. Then, there are 3 critical locations. One, the outer fiber, where you have sigma max, where your normal stress is, or your bending stress is going to be the max. 2, the neutral axis, where shear stress is going to be max, tau max. And finally, the web flange intersection for, say, W sections or etc. Wherever there's an abrupt change in the cross-section, you're going from a shear region to a moment region, that is usually a critical location that we need to check. Web flange intersection. Web flange intersection. Okay. And we're gonna, so let's see, I have to give you one more thing, here. And essentially what I'm gonna do is, for the rest of the lecture, I'm just going to be working through one example. Isn't this lovely? Yes. So that I have a very long example. It's going to take quite a bit of time to get through, but that's okay. So I have, when I create these lectures, I'm working through notes, and I have 4 pages of notes on this example. So it's going to take a while. Beam design, nobody said engineering was easy. Now, beam design. Now, thankfully, now we know that beam design tends to, or that we know that that a lot of engineering tends to be iterative. In other words, that you will run a design, then you find, oh, maybe the load will increase from the new weight of the beam, so you have to go back and check everything again, et cetera, et cetera. So design is an iterative process, analysis isn't. So often it helps to have rules of thumb. And for design, usually we design for Mmax. Design for Mmax. So especially on your standard regular types of beams, if you have something like built-up beams, like built-up sections that are made of like things like railroad girders and things like that, those have those are exceptions. But your general standard shapes that your standard hot rolled shapes that you're gonna get from a steel catalog, those are usually, if those are going to fail, they're going to fail in bending. So what we usually do is we actually just design for the Mmax. In other words, we find the location in the moment diagram that has the maximum moment, and then we just check it at the outermost fiber, because that will be so that is designing it for max bending moment. And we select a section based upon that, and then all we have to do is just go back and check all of these other things. So often it behooves us to just design for one condition. We still have to take all these things into account, but we design based on this. We select a cross section based on this, and then just merely check the rest of these. Check the rest. But then if you have beam analysis, you don't have to go through an iterative process. So your work is a lot simpler. Beam analysis, simply check the rest. Just check them all. Check all 3. Gotta check them all. Pokemon. No, wait, that's something different. So, beam analysis. Simply check them all. Just check them all. Okay. So, let us see here. We have a very long form example that will, this is going to be fun. It's going to be fun in the bun. So, just a second here. Yes, essentially all we're going to do is we are going to design a beam based off of the maximum moment, and then we're simply going to check it based on the rest of the design conditions, or based on the other of the critical locations, et cetera, et cetera. Okay, so I'm glad I'm only doing one lecture today. So this is example 1, and we're only going to have example 1 today, so I'll just call it example. Exemple. So consider this. Let's see here. So I have a beam here with the following 3-body diagram. Maybe I was given the loads, and then I found the reactions, etc., etc. So let's see. Here, I have the following. Load on here. So I have a long beam, very long beam. Very long beam means that bending will generally dominate. So thankfully it's going to be a simply supported beam, which I like, because I'm just a simple person. A little simple-minded, right? Okay. Anyway, so it's going to have a really fun set of loading on here. Just to make things hard, we're going to have a combination of distributed load and point loads. Isn't this lovely? good review for the exam. So we have a load of 0.1 pounds per foot, and then I'm going to have along it, I will have a couple point loads, maybe a 2 kip load here, just to start over, a 2 kip load here, a 2 kip load here, and a 1 kip load here. Then I'll need to provide you dimensions. And I will give you the reaction. I'll write the reactions and I'll write the dimensions. AY is 3.61 kips, and BY is 3.89 kips. Okay, now let us go and find our, let me list the dimensions, then we can actually get started on solving this. Here, and the dimensions are going to be 10 feet, 2 feet, 10 feet, and 3 feet. So this beam is not in any way symmetric, so it's a really annoying loading, but that's okay. And why you would have a beam like this? Well, oftentimes, we as engineers don't get to decide on the loading. If you have an architect that says I need a floor system like this, or I need a roof like this, well, oftentimes loads are just how they are, and you just need to make that work. So we can't always have nice symmetric beams, like in this case. So let us work through this here. I need to get the shear diagram and the moment diagram. Let us get the shear diagram and the moment diagram. So this is the free body diagram. Oh, and I should probably tell you what I want you to find. Let me do that. So now I could actually say we were just given the loadings and the length and the dimensions, and we had to find the reactions. But again, I think you know how to do that by now. So given this, find the most economical W section, I believe, yes. Select most economical W section. Select the most economical W section. Alright, so here, if I go up here, I'll need to draw the shear diagram. Shear diagram. This is why you learned how to design shear and bending moment diagrams in statics class, because this stuff's important. So we're going to have 3.61 kips here. That's why we learned it again in mechanics and materials. Then it's going to decrease down to, say, 2.61. I don't want to make it go quite that much. So let's do 2.61 here, 2.61 here, linear decrease. Then we're going to drop down to 0.61, 0.61. Then we'll be level for a while. Actually, no, we'll be slightly declining for a while. Slightly declining until we get to this point load, at which time we will have a load of 0.41, or sorry, a shear of 0.41 kips. Then we will drop with this point load down to negative 1.59, negative 1.59. Then we will linearly decline. I think I'm going to kind of draw some tracer lines. Yeah, I don't like how this is laid out. Just a second. I'm going to fix my diagram here. I like keeping everything at least a little bit lined up. So I'm getting a little bit off kilter as I go down. So drawing some tracer lines tends to help. even if my tracer lines are a little crooked. They're about the best I can do on the computer right now, without some better drawing tools that I probably should invest in, but we'll see. Whoa, what just happened? Did I just lose my tracer lines? Why did they go to this other slide? That's weird. Huh, where did my tracer lines go? Weird. Okay, sorry. Let me just, having some interesting issues with the program today. Let me draw my tracer lines down. There. Okay. So again, let me finish this shear diagram. I am going to have, why did those change color? Sorry, I'm having some issues with my, what? Okay, let me do something. This is, PowerPoint's behaving a little weird. Let me reboot it. Just a second, sorry about this. Okay, let me try that again. Just trying to draw some tracer lines, but it's giving me grief about it. Try just doing smooth lines, maybe that'll help. Maybe it doesn't like all those dots and dashes. Like here. Okay, so these orange lines, pay no attention to them, they have nothing to do with the actual diagrams, they're just lines to help me sort of keep things at least a little bit on top of each other, or lined up. So 3.61, then we linearly decline down to 2.61. I don't like how that looks. Down to 2.61 here. Then we drop down to 0.61. 0.61. Then we decline down again to 0.41. Then we drop down to negative 1.59. 1.59. Then we linearly decline to negative 2.59. Then we drop down to negative 3.59. Negative 3.59, and then we linearly decline down to negative 3.89. And finally, this reaction brings it back up to the top. Okay? Then I'm just going to kind of squeeze in the moment diagram below. And this is actually just going to be based off of, the moment diagram is going to be based off of just areas, and I think you know how to find that by now. The moment diagram, so M kip feet, is going to be, and V here is in kips. The moment diagram is going to be all parabolic. It's going to start at 0 and end at 0. And let me just give you the values here and try to squeeze it in here. It's going to be 31.1 here. Then it will be, say, this would all be parabolic if I could actually draw. It would be 32.12 here. 32.12 here. Then it will start declining. And it will get to 11.22 here. 1.22, but 11.22. And then it will linearly decline back to 0 here. 11.22. And all of these are going to be parabolic. So parabolic, 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 and parabolic. I know it was a bit messy, that took way too long, but that's okay. So to get this, that you just take the areas of each of these pieces, etc., etc. I need to look if I can see if anyone knows a way to putting like a grid on the back of PowerPoint slides automatically. That might help. I need to find a way to do that. Okay. I need to research that. There's probably a simple setting that will allow me to do that, but anyway, let's see here and there. I guess I could just put in images in there. That would probably work. Okay. So we said that we wanted to design based on max moment. So what that means is that we want to design for moment at the outermost fiber. So in other words, we're going to need to design for this 32.2 maximum moment. So let's see how we can actually do that. The issue is that, okay, we need to design for the moment of the outermost fiber, but what do we don't actually know the depth of the beam, do we? So we'll actually need to see how to work this. Design for moment at outer fiber. At outer fiber. Okay, what do we mean by this? So in other words, at the outermost fiber, the stress is going to be in a pure bending state. We're going to have tension or compression. I'll draw it as tension though. And sigma max is going to be M max C over I, or simply M max over S. And this S, we can actually, this is what we can use to find our beam. We can select a beam based on the S criteria. Okay. The section modulus. So say we have, so again, this is at the outermost fiber, this is what the state of stress is going to look like. It's going to be in, the principal stress is going to be our bending stress, or our maximum bending stress. So it's going to look like this, with this being 0, this being the sigma max that we calculated here, sigma max, this is tau max, and tau max, and here, then we got to base this again off sigma actual is less than or equal to sigma allowable, so we'll need to consider that, and tau actual is less than tau allowable, etc. Now, let's see. Could max shear stress, we gotta mask. We do have this shear stress. Even at the location on the outermost fiber, there's still shear stress, just based on different cut planes. Could max shear stress control? Shear stress control. Well, possibly, but we really want to keep, but for most materials, probably not. Sigma max over 2 is going to be tau max actual is less than or equal to tau allow, which is equal to sigma allow over 2. In other words, sigma max actual is just less than or equal to sigma allow. The same thing that we had before. So we don't really have any, it's this, here the shear stress is just going to be half of the, okay, what we really want to get at here is, here the shear stress is going to be, the actual shear stress is going to be half the maximum normal stress. The actual shear stress is going to be half the actual max normal stress. However, the allowable shear stress is actually half the allowable normal stress. So if one is good, the other is good. We really don't have to worry about it. We can actually we only have to worry about the maximum normal stress. So then, going forward, we can simply say M max over S is equal to sigma max actual is less than or equal to sigma allowable equals sigma fail over factor of safety. And for our purposes, we'll just let the, looks like parentheses, that's supposed to be an L, sigma fail. For our purposes, we'll just use sigma yield over the factor of safety. Okay? So let us say, we weren't told this explicitly, I don't believe, but let's just say our shear stress is 36 KSI. Or sorry, not our shear stress, our yield stress is 36 KSI. So we can reduce this to M max over S is less than or equal to sigma y, our yield stress, over our factor of safety, or S is greater than or equal to, so we need a section modulus that is ultimately greater than M max times the factor of safety over our yield stress. This is our guiding formula. And in this case, this is equal to 32.12 kip feet. This is from our moment diagram. This is the maximum moment at any location along the beam. Now do be aware, we do have to use consistent units. 12 inches per foot times 2.0, or let's use a factor of safety 2.0. You know what? Let me put that in the problem statement, because you probably would have been needed to be given that. Select most economical, W section, and then factor of safety. Let's be very conservative. Let's say 2.0, and let's say the yield stress is 36 KSI. Maybe this is good old-fashioned A36 steel. Okay, and all of this divided by 36 KSI for our yield stress. 36 KSI, kips per square inch, and this then comes to 21.41 inches to the third. Is in other words, I can say S must be greater than or equal to 21.41 inches to the third. So we need an S that will have at least 21.41 inches to the third. And so we just need to go to our table now. Got that? Okay. We're going to go to our table. You can find a good table in the back of your book, or you can look at the AISC. You can download that spreadsheet that we looked at earlier from the AISC. Just Google AISC steel table. Select sections from table. And if I list some, now let's say I went to the table and I found some sections. Maybe here are some possible sections. W8 by 31. In other words, what I would do is I would select some reasonable sizes. Like for each of these depths, I'm going to select the minimum. They're organized by depth, like W8, W10, etc. I'm going to go to the depth, and then I'm going to go to each family of beams, the W8s, the W10s, and from those, I'm going to select the one with because the way the table is organized, it's organized by family, and then within each family, they're sorted by weight, because W31, W32, W whatever, by the weight per foot. So to get the candidates of the ones I want to look at, I'm going to look at a series of families and select the lightest member of each family that has the minimum value of S. And so when I looked at the table, this is what I found. All of these had the sufficient values of S. W12 by 22, W14 by 22, W16 by 26, and W18 by 35. Now in our design here, we're only looking at the, saying the weight is critical, but in real engineering, the beam depth is also a critical design factor, like I mentioned. So, you know, if you can get away with the W8, even if it might be a little bit heavier, you might actually, see this one here? Notice this W16 will be able to carry the required S value, but so will this W8. Now, this one will save a lot of weight, a decent amount of weight anyway. You're saving steel by using this one over this one. However, the downside of this is that this beam is 16 inches deep. This one is only 8 inches deep. This is going to take a lot of floor space away from your building. So whether that's acceptable or not, it really just depends on your type of building. It depends on what your architectural needs are. There is no one-size-fits-all policy. If you are building a house, maybe W16 would probably be a little bit too much. If you're designing a big skyscraper, maybe the W16 is going to be just fine. It all depends on especially if you're designing like a big industrial factory. Well, if your ceiling's already 30 feet high, then who cares if you have a W8 versus W16? But if you're designing a building that's 30 floors high and the number of floors you can sell is directly related to the height of each floor, then you're actually really worried about the height of because if you think about it, if you think about a building, when we draw them as frames in structural analysis, we actually just draw them we draw them as line elements usually, but in reality it's not actually like that. Between each floor, there is usable space. There is the floor. If I think of a tall building with many floors, like this here, what I have here is really two zones. Maybe in the orange here, so these are floors and then walls, and floors and then walls. The orange is the useful space. This is space that you can actually that is livable. You can actually live there. You can whether it doesn't matter whether you're building a condo tower, doesn't matter whether you're building an office building, doesn't matter whether you're building apartments. You're building a building for a purpose. People, businesses, even warehouse space, whatever you're using this building for, this orange represents your usable space. The blue is only area that is needed to support and maintain all of this all of the useful space, whether you have, this is where you run your electrical cabling, your plumbing, your HVAC, all this other stuff, but it itself is worthless. The orange is the space that's usable. This is what you can actually, if you are a construction company or if you are a developer, this is the space that you can actually sell to somebody as a condo or it's the space that you can rent out to a tenant, either a business tenant or a residential tenant. This is the part that actually makes you money. This is the part that costs you money. So for a really tall building, there is a lot of incentive to minimize the depth. But anyway, we don't need to worry about that for this class. Let's just worry about weight alone. So often you would actually select you might actually select the W8, even though it's heavier than most of these, simply because it takes up much less space. But you know what? This is a mechanics materials class. Let's try to keep things simple. And as you've seen many times in this class, like many of your classes, as you climb up, but basically every time you climb the ladder to another level of class, you find that in your previous class they really padded it a lot and simplified things for you. Just like you've already seen that now when you're looking at in mechanics and materials, you learn that a lot of that in statics you made a lot of assumptions that you then can't make in mechanics and materials, and things get a lot harder. So that is sort of just the nature of the world. But anyway, that is a real tangent there, but that's okay. So for W14 by 22 here, let's say I go with this one is S equals 29 inches to the third. So here, 29 inches to the third here. This one would have a bit less depth, but this one has a better, these both have the same weight. However, this one has a greater depth, so this does have a better S. So this will actually give us, as long as we're ignoring depth, this one will give us a better strength for the same cost. If we're willing to ignore depth. Let's say we're, you know what, for our purposes, let's say this is a giant factory, it's a Boeing or a Tesla assembly plant or something crazy like that. It's, the ceilings are 50 feet high, and, you know, or maybe you're building, if you want to be less poetic or less inspirational, you can, it's a Walmart or something, you know. It's a building with a very tall ceiling, so we don't care about depth. Whether you have a 6-inch deep beam or a 24-inch deep beam, they don't care. It's all the same to them. It's only a single-story building, whatever. So depth isn't important in this example. We'll keep things simple. So let's just select a W14 by 22. We get more strength for same cost. But if I hadn't explained what I explained here, you might ask, well, if it's more strength for the same amount of steel, why the hell is anybody making W12s? Well, the answer is because in applications where depth is important, the 12 would have a lot of people would be willing to buy the 12, even though it's going to be less strength for the same cost, because you fit it in a tighter package. Okay. Well, I'm going to get off my soapbox. Okay. But anyway, just wanted to sort of give you some ruminations on the areas beyond just strength engineering. So now, so we now have, we've selected a section, and now from here on, we are just going to be checking it at various locations to make sure it passes various stress tests, or strength tests and stress tests. So check moment strength. So for the next check, I cannot talk. For the next step, I am going to check the moment strength. I'm going to check the moment strength. Here. So let us look at this. Well, let's look at that. You know, I'm going to do this on the next slide, I think. I don't think I quite have enough room for what I put on here, for what I want to put on here. So let's do that. Check moment strength. In other words, I'm going to check the total state of stress at the location of max moment. So I'm going to check that, and then let's look here. So I'm going to draw my Mohr circle and find, actually first I'm going to find my sigma max. Sigma max is equal to M max over S, which is going to be equal to 32.12 kips per foot, or kip feet, sorry, not kips per foot, kip feet, times 12 inches per foot, all over the the section modulus, which will be 29 inches to the third. And so this equals 13.29 KSI, which must be less than or equal to sigma allow, which equals sigma y over 2, that's our factor of safety, which is 36 over 2, or 18 KSI. So we are good. Okay. So then, let us look here. So I'm checking the location of, I'm just checking the moment strength right now. And our shear stress, our Mohr circle is going to look like this. Here is our Mohr circle. And it is like this. 13.29 KSI, 0, and then this is at the location of max bending moment in the beam, and this is 13.29 over 2 equals 6.65 KSI. And then let me go ahead and check the shear at that location. check shear here. Check shear. And so at this point, I want to make sure that I do want to go ahead and just check both the max moment and the shear. Tau max equals, it's going to be equal to 6.65 KSI, 6.65 KSI, which must be less than or equal to tau allow, which is equal to, well, our shear stress, our max shear stress is going to be sigma y over 2 over the factor of safety, which actually comes then to 36 KSI over 2 over 2.0, so which is equal to 9 KSI. So we're actually dividing the yield stress of the material by 4 to get the allowable shear stress, and we're good here. 6.65 is less than 9, but we're good here. So this does show you, though, that we do still need to check the shear stress at the location of max moment, because look, it's 6.65 and 9. That's close, relatively speaking. It's not like it was twice as strong as it needs to be or 5 times as strong as it needs to be. It's it could, if things had been different, maybe it would have been different. But anyway. So essentially, to review here, at the location of max shear, or sorry, the location of max moment, we checked the, so again, let me just recap. At location of max moment, check normal stress and shear stress. Thanks. Okay, so now we need to move on to a different location. So I'm going to check so I've now looked at the worst possible situation for bending. We have looked at the, in other words, look what we did here. We looked at the maximum location for bending. We went to the peak of the moment diagram and said, okay, we are going to look at the outermost fiber, which we have learned previously is the location of max moment bending stress, not max moment, max bending stress. So we have looked at both the conjunction of the location that along the beam line that has the maximum moment, and then the location in the cross section that has the maximum bending stress. So we've combined the absolute worst cases for bending. So we now know that this thing is fine for bending. It is not going to fail for pure bending. So, and that's what we designed for. But now that we have really thoroughly analyzed bending, let us check this thing for shear. So just like I took the, just as I took the maximum location along the beam for bending and the maximum location in the cross section for bending stress, I'm going to do the same for shear. And the corresponding state for shear is, I'm going to check the Vmax on the shear diagram, and I'm going to pair that with the critical location, the highest location of bending stress, which we know from yesterday is at the neutral axis. So I'm going to check it at the worst possible location, and if the most shear that this beam ever has to receive, if the material is not overstressed at the worst possible location along the cross section, then I know this thing is okay in pure shear. Is okay in pure shear. I will still need to check the a combination, which I will show you what point will be critical for combination. So then, here. Now, let us draw the cross section here. And all of this comes from a W14 by 22. It looks like this. It's a W section. If you call it an I-beam, you'll get in trouble. Alright, and let me show you the dimensions on here. So we might need that. Here we have now it doesn't look it by my drawing, but this is actually a symmetric section, so the flanges are equal sized. I know you can't tell by my crappy drawing, but that is the case. So the flange thickness is 0.335 inches. 335 inches. The flange width for both of them is 5 inches. The web thickness is 0.23 inches. And the web height is 13.07 inches. So note for all of these, we're going to use their actual values, not their nominal values. And we are going to cut this, so thankfully for this example, the neutral axis is right at the middle, because it's symmetric. So we are going to, for our shear, we're going to be considering the section above the cut, here. Or above the neutral axis, so our Q is going to be based off of this. And then the overall beam depth, if we need that, is from absolute tippy top to absolute bottom bottom is 13.74 inches. And we also have the properties IX is 199 inches to the fourth. Vmax, that's what we got from our, you know what, I don't want to write that as that. Maybe I'll just write this as red, because this is what we got from our shear and moment diagram. Vmax is 3.89 kips. And our thickness, our T, for our formula, T is going to be our web thickness, which is 0.23 inches. So remember in the shear equation we need the T. We're going to use the thickness of the section at the critical location. That critical location is the neutral axis. That is the thickness of the web, 0.23 inches. Moving along. Okay. Oh, I don't want to go next slide yet. I need to calculate our Q. This is going to be fun. Okay, let's get us a Q. So Q is going to be Q web plus Q flange, which is going to equal, for the web, 0.2. Remember, it's just it is just area for each piece. It's going to be the area times the distance of that thing's centroid to the neutral axis. 0.23 inches times 6.535 inches times 6.535 inches over 2. Over 2 plus 5 inches times 0.335 inches times, this is just a calculation of the centroidal distance, 0.335 over 2 plus the depth, plus the height of the piece of the flange that we have, this half of this, plus 6.535 inches. And all of this comes to 16.14 inches to the third. All right, moving along. The tau is going to be equal to, tau is equal to VQ over IT, which then plug and chug is equal to 3.89 kips, the maximum value from our shear diagram. 3.89 kips, see right here. If you can't read that, that's a 9. 3.89 kips. 3.89 kips times the Q that we got, which is 11 point, let's see, sorry, not 11, writing that number down, 16.14 inches to the third divided by the moment of inertia of the entire cross-section, not just the half above the neutral axis, 199.4 inches to the fourth divided by 0.23 inches thickness at our cut. And this is going to be equal to 1.37 KSI. All right, and then here, so I need to do another Mohr circle looking at this state of stress. And because there's no bending stress, this is actually going to be just a pure circle. This is actually just going to be a perfect circle, which I always draw, just a perfect circle, centered at the origin. And tau max here, let's see, this is going to be 1.37 KSI equals tau max, and this is less than 9 KSI, our allowable shear stress, so thankfully we don't have to calculate that again. Our allowable shear stress will be constant across, so we're good there. And then for bending stress here, or normal stress I should say, 1.37 KSI equals sigma max, and this is less than or equal to 18 KSI, our allowable normal stress, which we're good. And if I want to, I could also draw the stress block in this location at the cut plane that we're looking at, the orthogonal cut plane. It's just going to be in constant negative shear, like this, here, like this, here, like that. 1.3, and that's really sloppy, but I know, it's a very sloppy diagram. It looks really bad, but you get the idea. Okay. All right. Man, this is a long lecture. Okay. So, finally, I have one more location I wish to check. I have one more location that I wish to check. In other words, sorry about that. I have one more location I wish to check, and that is the combo location that I mentioned previously. So we have checked the critical case for shear, we have checked the critical case for moment. Now we need to check the critical combo case. So how do we possibly know where a critical location might be? Well, if we wanted to, we could develop a function versus height for all of these, and then find the combination stress. We could put the Mohr circle into this equation, then take the derivative of it, find where it's zero, and find maximums and sort of like that. But usually we don't do that. Usually we know from experience that there are certain critical locations. And from experience in this case, what we know is that we want to check the max M and V combo and V combo at the web-flange intersection. Web-flange intersection. That location is critical because that is the location where we know that the moment is going to be carried primarily by the primarily by the flange. So the bending stress is going to be have a decrease there because it's not necessarily a decrease, but it's not usually critical. But anyway, sorry, I should back up. We do have bending stress throughout, except at the center. But we know that the when you go from the flange to the web, your shear stress suddenly increases. So that's a discontinuity, a point of very sudden increase in your shear stress. So, you know what? In fact, I think I might just draw it out. Maybe that would make a little bit more sense why we're checking this location. Let me just draw this out instead of just trying to haphazardly explain it with all the clarity of a drunken monkey. So consider we're looking at this from the side, and I'm going to have my neutral axis at the middle, neutral axis here. And then, let's see. So I could look at the top or the bottom, it'll be the same. But just for fun, I'm going to look at the bottom. Because at that point it's going to be in pure, it's going to be tensile bending stress. I'm going to look right there. And why? And the distance to this is, for our particular beam, just for our particular beam, just for our particular section, is 6.535 inches. 6.535 inches. Now, our bending stress is going to look like this. This is our bending stress. It's going to look like this. So our bending stress just smoothly increases as you go along. That's our bending stress, just based on our strain and things like that. And then, but our shear stress is going to have this sharp discontinuity. Our shear stress is going to have this sharp discontinuity here. So let me draw the, maybe something like this. Let me show you the shear stress. Our shear stress, it's going to slowly increase, but then it's going to greatly increase at the web flange intersection. Then it's going to go like that. It's going to come back. Oh, that's bad. Oh no. That was all one line. Uh-oh. Then it's going to increase a bit. Then it's going to decrease. It's going to suddenly drop. And it's going to slowly drop back down to 0 at the edge. So this is our tau. So let's find the max. Let's find the shear and bending stress from each at this location from each of these. So let's see. Max V and M combo. So what do I really mean by that? Let's see. The shear value that I'm going to use is 2.61 kips. Which, let's see, so how do we get that, the 2.61 kips? Let's go back here and look at our shear diagram. 2.61 kips. That is not our absolute maximum value, but it is a point somewhere in the middle. So I'm looking for max values somewhere toward the middle of the beam because, how else to explain that? I'm going to use 2.61 kips, and I'm trying to come up with a good explanation why. I think just looking at this, so we're looking at the shear moment diagram. Here we have at the peak moment location, we have a high moment but a low shear. At the edges, we have a high shear but a 0 moment. This location is kind of special in that we have both a rather high shear, reasonably high shear, and a reasonably high moment. Not the maximum, but a reasonably high. So what I would really want to do is check these at various locations, but I will at least just illustrate how to check it at one location. So to really do this properly, you would have to check multiple locations, but I think if I show you how to check one combination, you would kind of get the idea. So at this location, along the beam anyway, sigma is going to be equal to my over I, and tau is going to be equal to VQ over IT. So what is our Q going to be based on? Well, since we're cutting at the web flange intersection, we're going to be looking at remember it is based on the outward area, so we're only going to be looking at the flange here. And the dimensions on this are going to be our flange width, which is 0.335 inches, 0.335 inches, and then we have the neutral axis down here, and the distance from the centroid of the flange to the neutral axis is going to be 6.5, actually no, it's going to be, well, let me just say, this is half our flange height, so this is 6.535 inches, but then the distance from here to here is actually the distance from the neutral axis to the centroid of the flange is going to be this plus half of this, which is going to be 6.70 inches. And that's going to be our y bar for our q. And q is then, if you do the calculation, simply equal to 11.22 inches to the third. All right. And now let me calculate my shear and normal stress. So this is going to be 31.1 kip feet, and then times that. Just do take great care when you're doing these. You do need to make sure to use consistent units. So I'm going to convert from inches or from feet to inches, times 6.535 inches, all over a moment of inertia of 199 inches to the fourth, and that equals 12.25 KSI. And our shear, our taw is going to be, or our shear stress, 2.61 kips. 2.61 kips, our value from our shear and moment diagram, or specifically our shear diagram, times 11.22 inches to the third, all over 199 inches to the fourth, times 0.23 inches. And this comes to 0.64 KSI. 0.64 KSI. And this is our stress element here. So we're going to have this, like this, and like this here. Positive shear, or sorry, negative shear actually in this case, I guess. Tau xy is going to be 0.64 KSI. Okay, tau xy equals 0.64 KSI. Okay. Then here, and we have sigma x equals 12.25 KSI here. Okay, for more circle, let's do more circle. Well, let's see. Our sigma average is going to be sigma x plus sigma y over 2, which is just going to be 12.25 over 2 equals 6.13 KSI. The radius of this is going to be just tau max, which is going to be sigma x minus sigma y over 2 quantity squared plus tau xy squared, and this equals 6.16 KSI. And then our principal stresses, sigma 1 is sigma average plus r, which is just going to be 12.29 KSI, and sigma 2 equals sigma average minus r, which is negative 0.03 KSI, and tau max equals r equals 6.16 KSI, equals r equals 6.16 KSI. And then if we compare them to our allowables, which is less than sigma y over factor of safety, sigma y over the factor of safety, and tau y over factor of safety, The allowables here then come to equal 18 KSI, 18 KSI, and 18 KSI. And these are good. So we just have one more thing I want to check. So we have completed this. We have completed the combination check. Oh, sorry. Yes, 9. I can't math. That's 9 KSI. Thank you. You know what? If I'm going to do this, let's do it right. Let's have the right color. 9 KSI. Trying to finish this up. Finally, I have one more. Check I want to make, and that is the average shear in web. Check average web shear. This is a critical one. Or can be anyway. So tau average equals V over TW times D. The shear from our shear diagram times the thickness of the web times D. Basically just the area of the web. Equals 3.89 kips. 3.89 kips divided by 0.23 inches times 13.74 inches. And this then equals, that's the overall depth of the beam. 13.74 is the overall depth of the beam. 13.74, it's the overall depth of the beam. We use the entire, we actually extend it into the web. We count this entire rectangle here. Because that portion of the flange is able to resist the shear as well, which is then equal to 1.23 KSI. And this is then less than tau y over the factor of safety, which equals 9 KSI. So we are good. So therefore, we can use a W14 by 22, and that concludes a single example of how to do beam design. And we're not even dealing with the advanced stuff from steel design class. So finally, I will give you just a few notes on this. Note: direction. Oh my goodness, I can't write today. Direction of M and V. M and V provide direction of sigma and tau. 2, you gotta be quick with the Mohr circle. Don't spend too much time on that. Must be quick, especially on exams and such. You must be quick with Mohr circle. So you should all be fairly practiced with this by now. 3, when trekking tau, if failure, what do? Well, you don't just want to add greater S. S is based off of your moment capacity. Instead, if you fail in shear, increase web area. Increase web, oh my gosh, increase web area. So look for a section with a greater web area. Then, what if you have a section that says, what if there is no flange web intersection, like just a simple rectangular beam? And what if you don't have one of those? Well, then simply check the max, just simply check it at the critical locations where the max combo occurs. check where max combo occurs. So go to the shear and bending moment diagram, select the location where the max combo occurs, and check it at 2 points, both at the top and at the both at the outermost fiber and the neutral axis, where max combo occurs. And that includes a brief lecture on beam design. So, all right, that will do it for today. It's quite a lecture, but that's okay. The final exam, if you're taking this class in this semester, the last exam will be on Friday. I will send an email out about that. It'll be on, not tomorrow, but a week from tomorrow on Friday. So on Monday, we'll be working through a lovely derivation of the deflection equation by integration, so that'll be all sorts of fun. But to do it, if you have any questions, feel free to email me. I have put, again for students this semester, I have put the partial credit grades for the previous exam on the website, so please check those out and email me if you have any questions. That'll do it for today. Have a good weekend, and as always, thank you.